Beneath the surface of the world's ocean, there is a carbon cycle we rarely see and even more rarely understand. Whales shape the ocean in ways we are only now beginning to learn. Each dive, each breath, each migration helps move nutrients through the water and influences how carbon circulates through marine ecosystems. These biological processes once operated at a scale we can barely imagine before industrial whaling removed nearly 3 million animals. As whale populations begin to recover, scientists are rediscovering the climate function that were diminished but not lost. Deep below the ocean surface, squid loom. Sperm whales dive more than 2 kilometers in search of these nutrient-rich animals. Once they are full, the whales return to the surface to breathe. Once near the surface, the whale then defecates. Their waste is rich in vital nutrients like nitrogen, phosphorus, and iron. These elements raise into the sunlit layer of the ocean, where even tiny pulses of iron can stimulate substantial phytoplankton growth. These microscopic algae absorb an enormous amount of carbon dioxide during photosynthesis, and studies have shown that whale-driven nutrient cycling can measurably increase their productivity. Because phytoplankton drive a major fraction of global carbon uptake, whales amplify one of Earth's most important natural carbon sequestration systems. In the Southern Ocean, iron limitation is one of the primary constraints on phytoplankton productivity. These primary producers are integral to the food chain, and a strain on them can strain the food chain further up. Southern right whales play a meaningful role in this nutrient-poor environment. A single defecation from a southern right whale can release 1 to 3 million times more iron than the surrounding seawater. These iron plumes stimulate local phytoplankton growth. Historical models suggest that before industrial whaling, southern right whales may have enhanced regional primary productivity by 3 to 7% through nutrient recycling alone. A similar process takes place when whales feed on krill. The nutrients released when whales drive important feedback loops. More whales produce more nutrients, which supports more phytoplankton increase krill, and more krill feed more whales. This upward spiral is a trophic cascade where whales indirectly boost the abundance of their own prey. Even in death, whales continue to move carbon. When a whale carcass sinks to the sea floor, we call it a whale fall. It delivers tens of thousands of tons of organic carbon to the deep sea sediments. These carcasses also create unique ecosystems and provide habitat and food for deep sea species for decades. Whale falls alone represent one of the most efficient natural mechanisms for long-term carbon storage in the ocean. Industrial whaling removed nearly 3 million whales, including hundreds of thousands of blue whales. This sudden loss disrupted nutrient cycles, reduced Southern Ocean iron recycling by over 80%, cut phytoplankton productivity, lowered krill biomass, and diminished carbon export to the deep sea. Restoring whale populations could return much of this lost ecosystem function. Estimates show that rebuilding historical whale numbers could increase the carbon sequestration by millions of tons of CO2 annually through both nutrient cycle and whale falls. Whales are more than large marine mammals. They play a key role in regulating the ocean's carbon cycle. Protecting whales restores this crucial ecological service and also supports ocean productivity and long-term carbon storage. Overall, this will contribute to a more resilient climate system.